estimators are random variables. We already saw that. Different data from the same data generating process gives a different estimate. So over here we have some data generating process. We define what the population quantity we want to know is, the estimand. And over here, if we sample some data and we apply our estimator, in this case it's a plugin estimator, we get this number. But if we change the data, we get a different number, right? But these data, it's not like one data set is better than the other. They're both samples from the same true data generating process. It's just that we got different people from the population. So our guess is going to be different. So that guess itself is random. So we can imagine what is the population of samples. So we have the population of people, right? The population of people induces some population of possible samples that we could have gotten. And for each of those samples that we could have gotten, the estimator has a value, right? So here's another way to look at that. We have the population. This is more mechanical. We have the population. We get we can compute the true value of the estimand. That's some fixed number on this number line. And again, if you're like, what are we talking about? Just imagine something concrete, like this is the expected value of some variable in the population. Now we have our data set that we sample, and we compute our guess of what that number is, say for example by taking the sample average of the measurement that we care about. If we had gotten a different data set, we would have gotten a different answer. And if we repeat this process for every possible data set we could have gotten from this data generating process, we would get this distribution of answers. And this thing here is what we call the sampling distribution of our estimator. So we've looked already at density functions for a while, right? And we normally write a density function like, okay, f just tells us this is a density. And then we put the little random variable here to tell us this is the density for this random variable. But now we're saying, well, this is the density of, this is not a measurement. This is not a thing that we're measuring for each person in the population. This is the thing that we measure for each data set in the population of data sets. And this has a distribution. So if that, okay, so this may be, let's keep going and I can circle back on that in a second. But the main idea here is that the estimator has a distribution, the estimate has a distribution of values, because if you had gotten different data, you would have gotten a different answer. And I keep hammering this because it's literally the most important thing in all of the most important concept in all of statistics, and also kind of the thing that is least understood by people who are coming, because you assume, well, that's the data are what's real, right? The data is what I have. That's what I get to see. Right? But no. The data is the tip of the iceberg, right? You don't get to see the whole population. You care about the population. And depending on where you're looking at the iceberg, you're going to see a different tip. And you have to think about what are all the possible answers I could have gotten, and how does that inform what the right answer actually is. So this is you can think of these data sets as all of them together, comprising the population of all possible samples from our original population of people. And here implicitly, I mean samples of a given size. So let's say this is the size of each of these data sets is 100. And then this distribution of estimates, you can think of like, you can calculate a probability from this by taking the area under the curve. And in this example, I'm showing you that this area is the proportion of samples where my estimate is between 1 and 2. So you can think, you never get to see this. This is imaginary. But you can imagine that if I had repeated my experiment, let's say I'm calculating some population mean. The population mean is really 0, okay? But you might imagine if 1,000 different research groups studied the same question and followed the same protocol, but they had different data sets that they were working with, how many of those research groups would guess that the population average is between 1 and 2? Some of them would, some of them wouldn't. And so what is that quantity? How many of them? That is what this area represents, and that is what the sampling distribution of the estimate is kind of giving you, right? Okay, problem is, It would be nice to have this, right? Because if we had this, this tells us a lot about what the right answer is, right? Because if it's a good estimator, maybe we're getting the right answer on average, and so we can say, well, the right answer is whatever this is. But we don't get to see this, right? We typically run the experiment one time. Maybe another research group runs a similar experiment later or something like that, but you already did the work, right? What's the point? So you only get to see the value that the estimate takes in a single experiment, which is why it's so hard for people to imagine all of this other stuff, right? That the underneath the tip of the iceberg, you just see the tip of the iceberg. That's it. And so the question is, how do you kind of infer about all this other stuff when you just see the one value you get? So here's a very concrete example. You have some unknown data generating process. In this example, it's very simple. I'm generating 100 samples from a normal distribution. What you get to see are those 100 samples. Here it is. And you're interested in the population mean. I can look at this data generating process right here, and I can tell you the mean is 0, right? But you just get to see this data, and you take the mean of the data, and it's not exactly 0, right? So here what we're doing is we're generating the sampling distribution of this. So again, this is grayed out because we can't actually do this in practice, because this depends on being able to repeat the experiment. So here I'm saying, what is my experiment? In my experiment, what I've done is I've collected data. So this is going to draw a data set of size 100. I apply the estimator. In this case, that's taking the sample mean of X. And then I put it in a table. What I'm doing here is rerunning this experiment 10,000 times. And then I'm collecting all of the estimates that I got. So that's this table here. So I see the first time I ran the experiment, my guess was 0.01. The second time it's 0.1, so on and so forth. So I could make a histogram of those values. That's what I'm doing here. So the dotted gray line is my histogram of all of the values that I got if I repeated this 10,000 times. The pink line here is the value that I actually got in that one experiment that I really did, not these hypothetical experiments. So you can see it's a bit different from, on average, I'm getting the right answer, right? But there's some likelihood that I'm getting answers, bigger than minus 0.25 or greater than 0.25, which is interesting, right? Because if you say, okay, how much, your question might be, how much should I trust the one answer that I get? If I did know this actual sampling distribution, you would know, well, I'm usually getting answers that are within, about 1/4 of the truth. So is that good? Is that bad? It depends on the question, but that here I might say that's okay. But you don't know that without the sampling distribution. You just get to see this. So that's the situation we find ourselves in. Another thing I want to clarify is that the sampling distribution is not the distribution of anything that you measure in your data set. So for example, here I'm making X. This is the measurement. So again, think X as height of people in the population, or the value of a biomarker or something like that. And let's say in reality, the distribution of that measurement in the population were this beta distribution. You probably haven't seen that before, but I'll show you what it looks like on the next slide. So that's a funky little distribution. And then what I'm doing is, besides that, everything else is the same. So I'm generating data from that, taking the sample average of X, and then I repeat the experiment 10,000 times and collect all the answers that I get. This is over here on the left-hand side. This is the distribution of X in our data. So this is the value of this biomarker, for example. So for this distribution might represent some biomarker that takes, maybe there's like a healthy population where the biomarker is very low. And then if you're sick, maybe it's like some inflammatory response and your body reacts. And so for sick people, it's very high. For healthy people, it's very low. And there's not very many people who have intermediate values of that biomarker. So this is the true distribution of the biomarker in the population. And here, these are the data that we actually got to see in the pink. So this is our 100 samples. This is where they fall. And you can see we're getting most of them over here in the left and on the right, but some values intermediate as well. On the right-hand side, this is the distribution of our mean. So I guess first let's talk about this estimate. This is literally just the average of these values. Okay, so if I average all of these dots, the value I get is about 0.51 or something like that. And this dotted line represents the distribution of the averages if I repeat this experiment 10,000 times. So you can see that this distribution, the distribution of the estimate, has nothing to do with the distribution of the random variable. I mean, it actually does in some sense, but it's not the same. That's not what we're talking about here, right? This is not the distribution of some quantity in the population. It's a distribution of some quantity in the population of samples. So I'll draw a picture to make that clear in a second, hopefully. But that's what we're talking about here. And notice that not only are the shapes different, but the axes are different too. So this biomarker takes values between 0 and 1, right? But the sample average that we compute from a data set of size 100 is somewhere between 0.4 and 0.6. That makes sense, right? If you have 100 samples that are kind of evenly distributed, here's not even, but they're distributed between 0 and 1, you take the sample average, it's going to be around 0.5, right? Every time, even if you repeat it, it's going to be somewhere near 0.5, and that's what this is telling us. So here, just to make it clear with some notation as well, this xi is the distribution of the measurement in the data set, or in the population, and then this thing here is the distribution of my estimate across different data sets. So this is another example. It's a little bit more complicated, but it's giving you the same idea. So here's an unknown data generating process. Now instead of a single variable, I have 3. So I have maybe some baseline covariate, an exposure, and an outcome. And I'm estimating the risk ratio from my sample of data. And then I repeat that experiment 10,000 times. And what I'm going to plot is the histogram of the risk ratios that I get. And then this is the just one of them is this line here. So let's actually take a pause for a second, and I want to show you what I mean by the distribution of a estimator. So let's go back to our population data set. Okay. So these are people. Each row here is let's say X, Y, Z, whatever. These are measurements in the columns, and each row here maybe represents a different person in the population. So we know what we mean when we say a probability or a density or something with respect to this population. We can say probability that X is less than 5. That is defined as the number of people where X for that person is less than 5. Okay, we're just counting up how many times did that happen in that population. This is my population of people. So from this population, let's say I'm thinking about experiments where I sample five people from this population. So in a single experiment, I might get these 5 people. So this is my data. This is my data set that I get in my single experiment. I could say what would happen if I repeated that, right? I would get a different group of 5 people, and a different group of 5 people if I repeated that, and so on and so forth, right? So these guys here represent a population, a different population. It's a population of possible data sets. So I can put them, let's put them into another table where instead of indexing on people, here I'm going to put, this is my sample that I got. So this is like my sample data set. Okay, so on and so forth. So this is like big N number of people, and this is actually going to be some very large number. For example, if we're considering sampling without replacement, It's like how many different ways can you choose 5 people out of a population that has n total. So this is some really big number. Or if we're sampling with replacement, then maybe it's a infinite, but a lot of those will be copies. However you want to think of how big this is, the main point to understand is that each row in this population is a data set. Okay, and what are the variables in this data set? Well, for each in this population data set, for each sample that I get over here, I can compute a number. So for example, I can compute the sample average of X, right? And I do the same thing here. These are different samples though, so we're going to get different numbers. So let's call this one psi hat 1, psi hat 2, so on and so forth. So the thing that I'm getting up here, the measurement, is psi hat, our estimate. So for each data set, I have a different value of the estimate. Okay. And the same way that over here, for each person, I have a different measurement of this biomarker or their income or whatever. So if on people we're measuring their income, on samples we're measuring the value of the estimate, and this is a population data set. So here I can ask things. I can say, what's the probability that the estimate is is less than 3? And that's just how many data sets were there. Let's draw like this. How many data sets were there where my estimate for that data set was less than 3? Okay. So same idea. It's just the unit of observation now is not these people, it's these samples or data sets. And we saw this in the very first lecture. We actually talked about, I think, or the second lecture, we brought this up, that populations don't have to be populations of people. It can be more abstract than that. They can be populations of something else where you're measuring something for each of whatever this thing is. In this case, the key to understand is that they're actually linked, right? So whatever this population is depends on what this population is, because the data sets are subsamples of this population. But so there is some kind of dependence on this distribution kind of induces this distribution over here. But nonetheless, they're not the same, right? So this whatever distribution this estimate has is not necessarily going to be whatever distribution this variable has in the population of people, because here the kind of, again, if you think of like a density or a histogram being as like, okay, I stack up all my people and I tell them to go stand wherever at the value of their variable is. So like this dude here had x equal to 10, so he stands here. This dude had x equal to 10, so he stands on top of the first guy, and so on and so forth. So this kind of represents the shape that you get when all these people go and stand around on their allocated places. Here, what we're stacking up is the data sets, right? So these are all the data sets where the value of the estimate was 4, for example. And then here's all the data sets where it was 5, and here's the ones where it was 2.5, and so on and so forth. So this distribution is kind of like counting different things. Hope that helped. It's a very important concept to understand. Like I said, the most important concept to understand is this idea of the sampling distribution. Also, one of the hardest things to understand for sure. Okay, so let's just keep playing with it. That's the way to wrap your head around it. Let's say that we have a binary variable that represents whether somebody is food insecure. And so 1 is if they're food insecure, 0 is if they're not. And let's say we want to estimate in the population the proportion of food insecurity, and the population here is people in San Francisco. I'm using a random sample of 50 people. And to estimate that population proportion, I'm using the sample mean estimator. So I'm just going to take the sample mean of the z in my data set. And I want to use R to plot what the distribution of our estimate would look like if the true proportion were these things. So how do I do that? Okay. The idea is just to follow the examples on these slides. So you set up, whenever you're doing this kind of thing, you set up what your unknown data generating process is. Then you specify what your estimator is, and then you repeat that process 10,000 times. That's how you build the sampling distribution. So those are the different pieces you need. So we can do that here. Let's just use this. So z is a Bernoulli random variable, and we want to let's say that the probability of getting heads of somebody being the true probability of being food insecure is 0. So this would be 1%, 0.01%. So very, very rare. Food insecurity is very rare. That would be nice. Okay, so if we want n equals 50, right? So here's the data that we might get. As you can see, it's all zeros, right? So the question is, we're estimating that proportion. So using the sample mean estimator. So what we're doing is just taking the mean of z. Okay, so in this one experiment, we get 0. We want to know if we repeated the experiment, what would happen. So we can take the data generating process and the estimator, and we can wrap that in a loop. So a couple of different ways to do that in R. I think rerun works. This function is kind of deprecated. So the way that they recommend to do it is with map. So what map does is you say, how many times do you want to do this? And you specify that as a vector. So 1, 2, 3, 4, 5. So I need to put in something like this. I'll just do it 100 times. So for input ranging from 1 to 100, I want to do this exact same thing. And if I just do it like this, it's not going to work, because what needs to go inside of map is a function. Okay, it's a function of whatever this input is. But I don't care what this number is. I'm just going to ignore it. So what I can write in here is a function of, I'm going to call it I. I is the iteration number, so that's going to be 1, because if you run this, you're going to get all these numbers, right? So for each of these numbers, this map function is going to do whatever you tell it to do in here. But it doesn't matter what I is. I want it to do the same thing every time. So I'm just going to say function of I, but then in this function, I'm just totally ignoring whatever I is. And do that. Okay, great. So now what that returns, you can see, is this long list. So for every input, so this is like input 7, input 8, input 9, 10, whatever, this is the value of that what happened in here. So this is, in our case, this is the estimate. This is the estimate in that experiment that we're repeating. This is outputted by default. The map function gives you a list object. Lists are a little awkward to work with, so there's a couple different things you can do. If you want to get a vector, you say map underscore DBL. DBL stands for double, or like number, basically. So if I run this, then I just get a vector of numbers out. So now this is something I could like put in a data frame, right? I could plop this into, I think this would work. Yeah, so now I have this in a data frame. So I have a data frame with one column called estimate, and then 100 rows. Let's go with this. Yeah. This little dot here, I think I mentioned it before, but this just says take what is ever on the left-hand side of the pipe and put it in here. So the output of this gives me a column, right? So I could have done this a different way. I could have said this, like, estimate is equal to that, right? And then in a separate line, I said, put that into a data frame. There we go. Same thing. I'm just kind of skipping the middleman. I'm saying whatever comes out of running this thing, plop that there. Same thing. Okay. So that's just some kind of coding details. Hopefully that helps make your coding a little bit smoother. This is now the sampling distribution of my estimate. But you may realize that this is really only the sampling. It's not really the sampling distribution, right? It's what happens if I run it 100 times. The true sampling distribution is if you make that infinite, right? But the general idea, again, of doing simulations is, okay, well, we can't actually have the true sampling distribution, but we can get pretty damn close by just making this number really big, right? So let's do that. Let's just make this number pretty damn big and run that, and it's going to take a minute. Cool. And, oh, well, of course, I totally wasted my time because I didn't save it. So let's just say save it. Make it a little more readable. And now we can make a histogram. And as you might expect, the vast majority of the estimates are near 0. Because it's hard to, when the population proportion of this, food scarcity or whatever or food insecurity is so small, in the vast majority of samples that you get, there's going to be nobody that's food insecure in that sample. And so your distribution of estimates is going to look something like this. So this is basically all the times that there was nobody, and these are all the times that it was a single person. 0.02 is 1 out of 50. So that's kind of interesting. Okay, so what happens if I change this number, right? Let's make it 1% instead of the 0.1%. Okay, that went through. Make the histogram. So now you can see it's changing, right? So now we have, still on the vast majority of samples, we're getting nobody who's food insecure, but now we're getting, in many samples, maybe half as many, we're getting a single person who's food insecure, and then in some samples we're getting 2, and in some samples we're getting 3 and 4 and 5, right? But more rare to see that. So let's push it even higher. Let's say you get 10% of people are food insecure. What is the sampling distribution? All right. Now we see there's a much more of a spread we're getting in these numbers, and you're seeing that you're clustering. Most of the answers are around 10%, but sometimes you're estimating 20%. Sometimes you're estimating 0% still, but on average you're getting about 10%. Awesome. So the hint here, and I just kind of dived in, but I hope that you're pausing this and you're actually thinking about it and trying it yourself before you're just watching me, because that's how you're going to learn best. If it's hard, that's good. It's supposed to be hard. You can't actually learn by doing things that are easy. It's actually just not possible. It has to feel like you're dumb. If you're not feeling you're dumb, you're not learning, which sucks, believe me. But that's how it goes. So I do hope you're trying. Here I said, okay, do this. So I could kind of simplify this. Here I was putting it in a very verbose way so that you could see the different steps, right? I set up my data generating process and I sample from it, and then I apply the estimator to it. But I could kind of wrap this up in a much more concise way. I don't need this whole data frame. I can just put the 50 in here. And I could just take the mean of this like that. Okay. And then here, a little shortcut for instead of having to write function, blah, 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 I can just write a little tilde. This is just a little shortcut for the map functions. It's not really that important. So this is the same. You don't need that if you're going straight into hist anyways. So let's try it just to show you that the simplified code works as well for if the proportion is half of people are food insecure. Let's do the same thing. Oh, what did I fuck up? Should work. See if this works. Yeah. Okay. Oh, right. Here, I just need a pipe. There we go. Right. So this is my sampling distribution. This is a shitty version of it because I only used 100 samples. So I can crank that up. And now I get something closer to what the true sampling distribution should look like. Kind of cute thing is that this code, by getting rid of all of that overhead, it actually runs so much faster. So it's something that you can consider doing in your simulations. If this looks uneven to you, right? Like, why is this left hand so much bigger? That's actually just an artifact of the way it's binning in this histogram. I think if I do breaks equals 30, it'll look nicer. There you go. Yeah. Cool. So this is the sampling distribution of my sample average. This also here shows you, the data themselves. If you look at the actual sample that I'm collecting every time, right? They're all ones and zeros. But then if you look at the sample average of those ones and zeros repeated over all the different experiments that I'm doing, that thing looks awfully a lot like a normal distribution, even though the original data are binary, not even continuously distributed. So that's low-key creepy.